Welcome to a lesson with Dr. Powell. We're going to take a look at how we can compute the derivative of quantity sine of x squared using a limit. Okay, and this will hopefully help us intuitively see the workings behind the derivative rule called the chain rule. But we're going to use a limit here. So to do that, we're going to look at 2 points in the domain of this function. We're going to call them x plus h, something close to x. H is just a little variance away from x, and h is going to be heading towards 0, and x. So between these two x values that we're going to be plugging into this function right here, we're going to get y values on that function. So we're going to get some coordinate points that are on the curve of that guy. By plugging in x plus h into the function, we get sine of x plus h quantity squared, and here plugging the x in, we get sine of x, and then that's quantity squared right there. Okay, so here's our ordered pairs. All right, 2 points on that curve. And to find the slope of the tangent line of this curve right at x, so I'm thinking of this as a function, maybe I'll put y equals. So in order to find the derivative, we find the slope of the tangent line, which is done by a limit. We find an average rate of change of the function between these two x values. That means the slope of the curve between these two coordinate points. And we're going to do that by doing rise over run. Think rise is difference of y values divided by difference of x values. So we have sine of x plus h quantity squared minus sine of x quantity squared. And all of that is over the run, so x plus h minus x, which is just h. And we're computing the limit of this as h approaches 0. All right, so that'll make this x value move to that one. The points move close together on the curve, and so little by little the slope will turn into the slope of the tangent line as we go, through that process of h going to 0. All right, so taking a look at this, how should we proceed? We're going to use a fact in this computation. We're going to assume that we already know what the derivative of just sine of x is. The derivative of sine of x is cosine of x. We're also going to assume that we already know what the derivative of x squared is. It's 2x. Okay, based upon those assumptions, we're going to find within our computation, we're going to find rise over runs that actually limit to these guys with maybe something else other than x plugged in. All right, let's see how that might work and how that might go. All right, so first of all, I see something squared minus something squared. Look what's inside of it. Inside here is one thing, so something's going to the x squared and something else, but aren't these close together? H is just a little away from x, so that makes this whole thing just a little away from that thing. Sine of x plus h is close to sine of x, so think of these guys as points. If you want, you can give them names. You can even call this like a, and you can call this w. And really, this is in this limit, what's happening? H is going to 0, but a is going to w as well. I mean, the two kind of work together. As h goes to 0, a will go to w. So this thing is going to that thing. All right. So wait a minute. So that top looks something like this. A squared minus w squared. So if you had like, hey, that's like a rise of something, of like this square function, the x squared function. If I had like a minus w, wouldn't that be a run? And then I'm inputting into the function. Hey, it looks pretty cool because I'm taking a limit as a goes to w. Shouldn't this part just go to the derivative of x squared with w plugged in, because a is heading off to that point, w point. So we're really finding the slope of the tangent line of x squared right at w. Won't this part just go to that derivative? Won't it just go to 2 times w? That would be really great. So let's use that idea here in this computation. All right. So kind of thinking about what we want to do. why don't we just divide by a minus w? We already have a squared minus w squared, so why don't we just divide by it? So divide by a minus w, which is, so we got sine of x plus h minus sine of x. But if we divide by it right here, we better multiply it by it as well. And we're going to see a crossing action here. So this divided by this, that's a squared minus w squared over a minus w. And we just said what that limits to. 2 times w, right? We're using this fact right here. Well, w is sine x. I mean, that's the point we're finding. So we're finding the slope of the curve x squared, where the input is actually, instead of x, the input point, depending on what the x value is just sine x. So sine x is going in to the function x squared, and we're finding the slope of the curve x squared at that point. Well, it's just 2 times that point, that x value. So 2 times sine x. So this part of the computation just limits to 2 times sine x. Now look at this other cross piece. See what this is? This is using the interpretation of x like we did up here with x plus h and x, and this x value closing into that x value. This is a rise, and the run, x plus h minus x, is just h. Oh my goodness, this looks like an average rate of change which is approximating the slope of a tangent line on this graph of sine of x. At the point x, hey, that's just the derivative cosine x. This part's just cosine x. That's what it limits to, as h heads off to 0. Wow, so what do we got? We got cosine x. In fact, we can move that h over here and that over there, but it's just going to be multiplied together. So basically, it's just these two things multiplied together. Cosine x times that guy. We can write it down as 2 sine x times the cosine x. So what we've done, quite literally, is we take a look at this guy. We're squaring. This is a square function. And think of, I'll leave this blank. Think of variable. What's the derivative of variable squared? Well, it's 2 times variable. But since the variable was not x, then we have to multiply by the derivative of a variable. At least that's what this is telling us, this cross action. The derivative of the variable is right here. It comes from the crossing. And the derivative is cosine x, because our variable was sine x. Thinking of sine x as being a variable if you want. So that is an example of the chain rule, but via a limit computation with sine x quantity squared. Really, the limit computation is not too difficult to write out and see, and it actually intuitively shows exactly what we want, which is, this is the chain rule for derivatives. Thanks for watching.